to another session on molecular orbital theory. Molecular orbital theory can help us understand the bonding situation in different types of molecules, whether they are homoatomic molecules or they are heteroatomic molecules. We have discussed the basics of molecular orbital theory in the previous session. Today we will try to apply molecular orbital theory to some simple molecules and see how this theory can explain the bonding situation, the bond orders in different types of molecules. So first of all, we will try to apply this theory to beryllium. Beryllium, it belongs to the second group and its atomic number is 4. And that means that its 2s orbital has 2 electrons. That means that its 2s orbital is complete. So if we assume that beryllium is going to form a bond with another beryllium atom, if we consider beryllium as Be2, just like O2 N2, if we consider beryllium as Be2. So let's see if molecular orbital theory can help us in explaining the formation of this molecule, Be2. So you can see that the electronic configuration of beryllium is 1s2, 2s2. Now this 1s orbital, because it's a lower energy orbital, and we assume that it is not involved in chemical bonding. So the valence electrons are actually involved in chemical bonding, and that is why we will only consider the 2s electronic configuration or the 2s electrons of beryllium for forming a bond with another beryllium atom. If you remember from the last session, that molecular orbital theory states that atomic orbitals combine to form molecular orbitals, and this is explained with the help of an approximation which we call the linear combination of atomic orbitals. And so this combination of atomic orbitals leads to the formation of molecular orbitals. And the number of molecular orbitals formed as a result are exactly equal to the number of atomic orbitals that combine to form these molecular orbitals. So we will see in case of beryllium how many atomic orbitals are involved and how many molecular orbitals are formed as a result, and what would be the bonding situation at the end of this process. So again, let's draw the molecular orbital diagram for beryllium on an energy scale. So we have the 2s orbitals of beryllium now involved in bonding. We will not consider 1s because you know that it is not involved in bonding, so only the 2s orbitals are involved. So this is the 2s orbital of one beryllium, and this is the 2s orbital of another beryllium. Now you know that the 2s orbital of beryllium has 2 electrons. So each of these 2s orbitals is filled with 2 electrons. And now you know that we have 2 orbitals going to form a bond by overlapping or by combining together. So when 2 atomic orbitals are involved, it will give rise to the formation of 2 molecular orbitals. And one of these is known as the bonding molecular orbital, and the other is known as the anti-bonding molecular orbital. S orbitals, they are spherically shaped, and so they will overlap head-on, obviously, to form sigma bonds. So this is the sigma bonding molecular orbital of beryllium, and this is the sigma star anti-bonding molecular orbital of beryllium. Now let's place all the electrons in these molecular orbitals. So we have in total 4 electrons. You start filling from the lowest energy orbital. So 2 of these electrons go into the sigma bonding molecular orbital, and 2 will go into the sigma star anti-bonding molecular orbital. Now you know from the previous session how to calculate the bond order, and that will actually tell you the bonding situation in a molecule or in an element. So bond order for beryllium would be half of the electrons present in the bonding molecular orbital, that is equal to 2, minus the number of electrons present in the anti-bonding molecular orbital, that again is 2. This is equal to 0. And this shows that the bond order for Be2 is 0, which in other words mean that the formation of Be2 is not possible. So there is no bond between two beryllium atoms. And that is explained here with the help of the molecular orbital diagram of Be2. Be, beryllium, belongs to the second group, so it belongs to the S block. Now let's move on to the P block. In the P block, the first element is boron. Boron has an atomic number of 5. Let's see how molecular orbital theory explains the bonding situation in boron. So now in boron we have 5 electrons in total. 2 of the electrons are present in the 1s orbital and the rest of the 3 are present in the 2s and the 2p orbital. 2s has 2 electrons and 2p has 1 electron. And as you know that the valence orbitals are always involved in chemical bonding, so again we will ignore the electrons or the orbitals that are deeply seated, that is the 1s orbital. We will only be playing with the electrons present in the valence shell, that is the 2s and the 2p electrons. So let's see how the 2s and the 2p orbitals of boron will be involved in forming bonds. So again, let's draw the diagram on an energy scale, and first we have the 2s orbitals that are lower energy orbitals of boron. And these 2s orbitals will give rise to the formation of 2 molecular orbitals. Again, a sigma bonding molecular orbital and a sigma star anti-bonding molecular orbital. But then we have the p orbitals as well. Now these 3 p orbitals, the ps, py and pz, have only 1 electron, and you can place them anywhere. Now we have 3 atomic orbitals from one boron and 3 atomic orbitals from another boron. So in total we have 6 atomic orbitals, and you know that as a result we will have 6 molecular orbitals as well. So you can see that now we have 6 molecular orbitals. Let me draw them in a different color. You can differentiate between them. These are the 6 molecular orbitals. Now, how do we name them? So these 2 here are the pi bonding molecular orbitals, and this is the sigma bonding molecular orbital. If we have 2 bonding pi molecular orbitals, we will also have the 2 anti-bonding pi star molecular orbitals as well, and we will also have a sigma star anti-bonding molecular orbitals. So now you can see in total we have 1, 2, 3, 4 plus 4, 8 atomic orbitals, and as a result what we have now is 1, 2, 3, 4, 5, 6, 7 and 8 molecular orbitals are also formed. The next step is to accommodate all the electrons present in this valence shell in these molecular orbitals. So let's start filling the electrons. So the 2s orbitals of both the borons have 2 electrons each, and p orbital has only one electron. So let's start filling the orbitals. So in the 2s we have 4 electrons. You start filling from the lowest energy orbital. 2 electrons go into the sigma bonding molecular orbitals and 2 electrons go into the sigma star anti-bonding molecular orbital. Then we have the p orbitals. So we have a total of 2 electrons. And you know from Hund's rule of maximum multiplicity that if we have orbitals of equal energy present and we have more than 1 electrons, you do not place them in the same orbital with opposite spins, but in fact you place them separately. You place them singly in 2 different orbitals with the same energy, and these electrons will have the same spin. So these 2 electrons will go and occupy both the pi molecular orbitals. They will not be placed in a single pi bonding molecular orbital with opposite spins, but rather they will be singly placed in both the equal energy, the degenerate pi bonding molecular orbitals. Another interesting feature of this molecular orbital diagram is that you can see here we have 3 p orbitals from one atom, 3 p orbitals from another. So in fact we will have 6 molecular orbitals. 2 of them are the sigma and the sigma star, and 4 of them are the pi and pi star molecular orbitals. Here the pi bonding molecular orbitals have lower energy as compared to the sigma bonding molecular orbital. And so the sigma star will have the highest energy and the pi star will have lower energy as compared to the sigma star anti-bonding molecular orbital. So when you are going to place electrons, they will go first into the pi bonding molecular orbitals and they will have similar spins. Now this has been proven experimentally with boron. Boron does not have a sigma bond, but it has a weak pi interaction between the 2 atoms. That again, as I said, is proven experimentally, and this is also clear or visible from this diagram that these unpaired electrons are not present in the sigma orbital, but in fact they are present in the pi bonding molecular orbital. So we cannot define the energy criteria for filling out these orbitals, and that means that these pi orbitals will have lower energy as compared to the sigma bonding molecular orbital. So in fact you can expect the formation of this P2, but that will not have a sigma bond. In fact it will have a weak pi bonding interaction between the 2 boron atoms. Now let's see another p block element, that is nitrogen. So nitrogen belongs to the 5th group, and you know that it has 5 electrons in the outermost shell. Again, the 1s orbital is complete. We're not concerned with that. But the 2s and the 2p orbitals will be involved in bonding. Now you can see that the 2s orbital has 2 electrons and the 2p orbital has 3 electrons. So a total of 5 electrons are present in the outermost shell. Now let's see how molecular orbital theory can explain the formation of N2 with the help of the same diagram. So again we have the 2s orbitals completely filled. This is similar from the previous example. So we will have 2 atomic orbitals combining to form 2 molecular orbitals, the sigma and the sigma star, bonding and anti-bonding molecular orbital. Both will have 2 electrons each, and that means that the sigma orbital is not involved, or the s orbital is not involved in bonding. Let's move on to the p orbital. Here we have 3 electrons in the p orbital, and you know that if we have degenerate orbitals, we have similar energy orbitals. They will have single electrons with similar spins rather than paired spins. So now we have in total again 6 atomic orbitals, 6 molecular orbitals will be formed as a result with the same energy profile on this energy scale. The pi bonding will have lower energy, the sigma will have higher energy, and then we have the pi star anti-bonding and the sigma star anti-bonding molecular orbital. But now we have 6 electrons, 3 from each nitrogen, and we are going to fill these orbitals with these 6 electrons. So, we're going to fill these molecular orbitals with the 6 electrons that are present in these atomic orbitals. So, let's start from the pi bonding molecular orbitals. We have 6, so you place 2 electrons separately first, and then you have to pair electrons because we have more electrons present. So now we have a total of 4 in the 2 pi bonding molecular orbitals. We are left behind with 2 more electrons, and those 2 electrons will go into the sigma bonding molecular orbital. And as you know that nitrogen or N2 has a triple bond between the 2 nitrogen atoms. One of those is a sigma bonding molecular orbital, or one of them is a sigma bond and the other 2 are the pi bonds. And you can see here that we have sigma electrons and then we have 2 pi bonding molecular orbitals having 2 electrons. So that can clearly explain the formation of a triple bond between the 2 nitrogen atoms. Now let's see oxygen, and that is interesting. So oxygen belongs to the 6th group. It is also an element that belongs to the p block, and so you can see that the last electron goes into the p orbital. Again, the 1s orbital is completely filled, that is not involved in bonding, so we will only consider the electrons present in the 2s and the 2p orbital. 2s has 2 electrons, so these 2 atomic orbitals will form 2 molecular orbitals again, similar to the previous examples. And because we have 4 electrons, so both the sigma and the sigma star will have 2 electrons each. But now we have the p orbital with 4 electrons, and you can place them in this form. And again, we have 6 atomic orbitals. 6 molecular orbitals will be formed. Let's see how they look like. Right, so these are the 6 molecular orbitals from the p orbitals of both oxygens, and now you see that the sigma bonding molecular orbital has a lower energy as that of the pi bonding molecular orbitals. And here we have the anti-bonding pi star and sigma star molecular orbitals. Now we're going to place electrons in these orbitals. So we have in total 8 electrons. You start filling from the lowest energy orbital. So we have 2 electrons in the sigma bonding molecular orbital. Then we have 1 electron each in the pi bonding molecular orbitals because they are of equal energy. But we're left behind with more electrons, so you can pair them up. So 2, 4, and 6 electrons. But in total, we have 8 electrons. And those 2 electrons go into the equal energy pi star anti-bonding molecular orbitals. And now you see that oxygen has 2 unpaired electrons in the anti-bonding molecular orbitals. The energy profile diagram shows that the sigma bonding molecular orbital is of lower energy than the pi bonding molecular orbital. That is different from what we saw for nitrogen, for example, in which the pi bonding have lower energy than the sigma bonding. It is because of the fact that oxygen being more electronegative and there is a larger nuclear charge that attracts the sigma bonding molecular orbital more tightly, and that is why it goes lower in energy than the pi bonding molecular orbitals. That is not in the case of nitrogen or boron that we discussed earlier, but in case of oxygen and in halogens as well, because of the larger nuclear charge, the attraction is so much that These sigma bonding molecular orbitals, they go down in energy, and so you can draw this molecular orbital diagram in this form. Right, so these unpaired electrons in the antibonding pi star molecular orbital of oxygen are responsible for the paramagnetic behavior of oxygen. Before this, valence bond theory could not explain the paramagnetic behavior, but molecular orbital theory can give you an insight into the paramagnetic behavior of oxygen, just because it shows that it has unpaired electrons and it can be influenced by external fields. So if you want to calculate the bond order for oxygen, you see here we have 2 electrons in the sigma, 2 in the sigma star, 2 minus 2 is equal to 0, this is equal to 0, so you go and check the p orbitals. So we have 2, 4, 6 here, 2 here, and you take half of that. 6 minus 2 is equal to 4, 4 divided by 2 is equal to 2, and that means that O2 will have a double bond between the 2 oxygen atoms. So this is how you can explain the bonding situation in different molecules. These were some of the examples of the homoatomic molecules, and you can also apply the same concept to heteroatomic molecules like the bonds between carbon and oxygen and carbon and some other molecules as well. And this molecular orbital diagram also helps in calculating the bond order, so you can exactly tell how many bonds are present between the 2 atoms. In addition, in case of oxygen, it also tells you about the paramagnetic behavior of oxygen, that is because of these 2 unpaired electrons. So this is it about molecular orbital theory. I hope it helps you. Thank you so much. We will discuss some more topics in the upcoming sessions. Thank you for now.